Okay, so hello everyone. My name is Junqi. I'm a staff member at NICS, and welcome to the seminar series on HPC. And today I will be talking about HPC in physics. My specialty is in condensed matter physics, and later Reuben will be talking about astronomy physics. So the outline of my talk. First, of course, the motivation. Why do we need HPC? Why do we need to use high-performance computing in physics? And then I will talk about there are two approaches to use HPC commonly. First one is using numerical methods, like doing numerical calculation like solve PDE or doing matrix operation, etc. And versus computational simulational methods. And then I will talk about two common methods in simulational physics. One is molecular dynamics. The other one is called Monte Carlo method. After that, I will show a case study for a code named WLLSMS. It's a first code that can do finite temperature ab initio calculation on a large scale. Then I will summarize. So we know that traditionally there are two research methodology when you study nature. First one is a theoretical study. The other one is experimental study. And after the emergence of the computer, now there are the third pillar they call simulation method. So if you do a research, you search online, you can see a lot of studies doing simulational using simulational methods. That's because fundamentally there are just very limited problems that can be solved exactly using analytic methods. You need to resort to the simulation. We all know that for three-body interaction method, three-body interaction problems, there's no exact solution already. So we have to rely on computer simulation. And these three methods actually are related, because simulation, first, to confirm your simulation method's correctness, you need to to compare with experimental results. When you build your simulation code, you need to develop either a numerical way or a simulational way based on the theory you understand about the experiment. Then you do the simulation, which can be confirmed from the experimental results. So why do we need HPC in physics? Okay, I just show you here a problem. It's a very simple one. Let's say we want to study water, H2O. On the top right corner, I show a simple view of water. It's like view the atoms as a point, basically a point mass in this view. So in this simple model, we basically model the interaction between oxygen atom and two hydrogen atom using Coulomb force, and there are several models for this classical water molecule. We called it SPC/E or tip 3P or tip 4P. These potentials you can just search online. That's how people model water molecule classically. And if you want to solve water molecule, let's just ask the question: if you put a bunch of water molecule together, what kind of structure will they form? Like, I mean, what kind of structure is the most stable structure? To answer that question, you need to like minimize minimize the energy for this structure and search for a ground energy. So this is like a global minimization problem. We know that it's NP hard. There's no exact solution here, and it's even for like 20 to 30 molecule I show here is already a challenge uh, for 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 computing, because there are just so many state. You can the search state, the search space is huge. If I can show you the diagram on the left side, on my left side on the right, you can see that I plot the density of state for water molecules. What I mean by density of state basically is the degeneracy of energy state. I mean, for one specific energy, let's say if you look at x-axis, if for one specific energy, how many different structures could this structure have? I mean, how many degenerate state could have the same energy? Basically, if you see the plot is actually in logarithm scale. So for the bottom, for the curve, I show the numbers here. You can see it's the logarithm scale. The number of states for water molecule with 30 number of water molecules is 2 to the power above 2 to the power 600, which means for 30 water molecules, if you put them together, there will be like 4.15 multiplied by 10 to the 180, this number of possible structure it can have. So to search for the ground state, if you want to have a complete picture of these structures, basically you need your code. You need to update the structure this many times, basically. So this basically shows that why do we need HPC? We cannot because in real problem the size will not be like a 30 water molecules. That's nothing in a real system, right? So how do you do performance simulation using high performance computing? There are basically two ways. You either for your problem you can do numerical methods. For example, there are a lot of well-developed numeric libraries you can direct use. It's like a drop-in approach. So in your code, say you need to solve some partial differential equations or something like that, you can just use well-developed libraries. Here on the left side, I show statistics for some library usage on our system Kraken and another system, previous system on the lab. You can see that those packages are heavily utilized, such as libsci, Cray, Science Library, FFTW for fast Fourier transform, etc. So if your code simply to solve some equation, for example, need to do Fourier transform or need to solve a PDE or need to solve a matrix problem, eigenvalue problem, you can use a drop-in approach by calling these libraries well-developed libraries. And if you look at the CPU usage, on previous Kraken machine of NICS and the Jaguar of the lab, you can see that most of time have been used by this physics code. On the top right side, this P gadget is, I think, is an astronomy code, and on the bottom side, the average used per run. It shows that this HMC, which is a Monte Carlo code, it has the highest usage for the number of core used for this run is huge. You see, it's on the order of 10,000. And if I don't show you the statistic of CPU hours utilized by codes in different area, but most of, I think, over 60%, if I remember correctly, for the inside resources are used by actually physics code. In this sense, physics is actually one of the first fields that use HPC, traditional HPC field. And how do you do so? The most two common methods utilized in this simulation are solving a physics problem, molecular dynamics, or Monte Carlo simulation. So let's look at this problem. Say you have like several hundred argon particles in a box. This is, I think, a straight, simple problem because argon particles are not that the interaction between argon particles are basically neglectable in this case. And how do you solve this problem? If you ask, like, what's the average velocity, what's the average like distance between atoms, what's the average energy of this system. So there's two ways you can solve it. For example, if you want to do molecular dynamics, first, in a classical way, you just list the Newtonian equation for the system, and basically by given the Hamiltonian, which is first part is the kinetic part, the second part is the potential part, potential energy, then you solve it like you solve a Newton equation, second equation for each atom. So you update the, so you start from an initial position, and all the position, velocity, and acceleration for every particle can be solved by solving the Newtonian equation. Then you know exactly what's the position of each particle at time t plus delta t. So in this way, you can have the velocity after system equilibrium. You can know the velocity of every atoms and the position of every atoms. So you know you can do a simple statistics and get the property of the system, like energy and etc. This is how you do it in molecular dynamics. So if you want to solve it in Monte Carlo simulation, in this case, for Monte Carlo, the dynamics is artificial. It's not a real Newtonian dynamics. You update the system in a way that can achieve detail balance, but it's not a real physical dynamics. What you care about is sampling. So for this system, if you don't care about, like, let's say you don't care about exactly trajectory of one atom, particular atom, you just care about an average quantity. Let's say you want to, you care about average velocity or average something, you can just using Monte Carlo method. In this method, there's no kinetic part. So if you compare the Hamiltonian on the right side and the Hamiltonian on the left side, in Monte Carlo simulation, we only care about the potential energy of the system. and we update the system in a way that you just randomly pick an atom and move it to another position. Of course, whether you accept this move is according to a desired ensemble you want to achieve. For example, if you want to do canonical ensembling, which is a distribution follow Boltzmann distribution, then you simply just update or reject the move by this transition probability from H state to H prime state, which takes probability basically according to the Boltzmann factor. So it's proportional to the reversely. So if the move lower your energy, you accept it. If the move gets your energy higher, you accept it to e to the power delta E divided by the kt, so which is a Boltzmann factor. This algorithm is actually called Manchoplik's algorithm. If I remember correctly, this algorithm is actually one of the top 10 algorithms in 20th century. Among the list, there's a fast Fourier transform, if I remember. So it's actually a way to achieve any kind of distribution you desired. So you have a system, let's say you wanted your system have some kind of distribution, then you can using Manchoplik's algorithm, which is driven by Markov chain Monte Carlo, to achieve this desired distribution. After system equilibrate, you just do sampling. So from the way I describe these two algorithms, you can see that molecular dynamics is not a intrinsic parallel algorithm, because you do it time by time. Each time you increase the time by delta t, which means that it's dependent, it's coupled. So what you parallelize is basically parallelize the part where you calculate the, let's say, the force for every atom. You can calculate the force, the move for the next move, for the next potential move parallelizely. But for Monte Carlo, it's a sampling method. So it's an intrinsically parallel algorithm. When you do your research, you need to basically consider these two methods you can use in your bag of trick. So there are actually some popular code you can use directly, especially for molecular dynamics code. For example, there's NAMD code, which has been used in biophysics. Also in biophysics, this LAMMPS code. So if you're interested in biosystem, like doing protein folding, for example, you can try this code. VASP is another MD code that can be used to solving ab initio. If you study some material, you want to do a first principle calculation using some ab initio method, you can use VASP package. These popular packages are already installed on most high-performance computing platforms, for example, at NICS. For MC, there are less popular code because MC is conceptually very easy, and it may depend on specifically on your problem. But if you are interested in solve a quantum Monte Carlo problem, there's a QMC pack. A Monte Carlo simulation can be also applied there. And there's a code called MCCCS, which is using Monte Carlo for complex chemistry system. So, but generally, MC code can be developed specifically for your problem, because what you call the Monte Carlo simulation is a very general term. It's not like, so basically any code that involve a random number experiment. Basically, it's like a random number experiment then you can call it a Monte Carlo code. So if you want to look at what kind of code installed, you can go to our website. Okay, now let's show you example high performance code that are actually used on computing. So it's actually a code to study magnetic properties of metals or alloy at finite temperature. So it has two components. So we know that most of these ab initio codes just solve for ground state of your material, and so for that part, for the ab initio part, it's called LSMS. Basically, it solves Cauchy equation, and it's solve the electronic structure of your system. And the second part is an algorithm called One-Landau method. It's a popular method since 2000, and people use this method. It's a algorithm that can be used in Monte Carlo simulation. It's not a traditional canonical ensemble sampling, but rather a generic ensemble. It converges fast. So if you consider static sampling, you might want to try this One-Landau method. So to study finite temperature of a magnetic system, let's say iron, basically you want to combine the thermodynamics calculation with the first principle calculation. So this code is doing exactly that. It has a common architecture. You can see for parallel code, it has a master node which do thermodynamics, and a worker node doing the first principle calculation. This code achieves amazing performance on the labs on the ORNL's supercomputer. As you can see, actually this code won the best performance for high performance computing code. And if you look at the scalability of this code, basically it can scale to the whole system, like hundreds of thousands of cores, scales up to full scales of the system, and even using the full scale system, the number of atoms you can study are still at 1,000 level. So currently, the cutting edge software, you can study the magnetic properties. How many atoms can you study? Like on the level of 1,000. There are results that you study up to like million atoms, but that basically they use some tricks and not absolutely from the first principle. Okay, here is some results from the iron. We know iron is a magnetic material, so we can apply the previously mentioned code to study iron. So how do you do that? Okay, we know we know basic theory. The code is there. It's based on that. And for the top left, I show the experiment data. So from the experiment, you do the measurement. You can have the specific heat, which is a thermal response function for the iron. You see a singular point here where it shows a huge peak. That's where the transition happens. When the temperature below that temperature, your iron is magnetic. When the temperature is higher, there's basically there's a paramagnet, so your magnetic disappears, moment disappears. And here is results from our calculation. Previously in study, people don't consider the vibration of atoms. That's too microscale. right? For this system, people don't consider the vibrates of a single iron atom, but in fact, such vibration will have a contribution to the magnetic moment. If you want to study the magnetic property of iron, you need to actually consider the vibration of the atoms. Here I show you a vector plot where different color for the arrow indicates the different magnitude of magnetic moment. As you can see, because the vibration, because of the displacement, the magnetic moment in the actual iron system is not uniform. There follows a distribution here. If you in the left lower plot, I show for the open circle, red circle, that's the results without considering the vibration, lattice vibration. You see, there's a discrepancy between the red circle and the black square, which is experimental results. Once you consider the lattice vibration, which is shown as the downside triangle, you see the result is consistent with the experiment. That's how you use simulation to understand a material, to prove your theory. That's basically shows the whole cycle of HPC application in physics. So in summary, the scale of you see the scale of the problems in condensed matter physics, right? It absolutely requires HPC. Without high performance computing, you cannot solve these challenges. And there are two types of approach, depends on your problem. If you just simply solve, if your problem, you can solve it in a way that is definitive. If you know the equation to solve, if you know, you just transform it into some equation, solving some equation or solving some matrix problems, then you can use directly numeric method. There's another way you can also use computer experiment, which is like a simulation way. So the two popular methods, one is molecular dynamics, which is, and the other is Monte Carlo simulation. But still, the results I show you, you see that even with the most advanced HPC, we can still just solve like a system consists of thousands of atoms at this stage. So there's still a lot of work to do. There's a way you can contribute. Thank you for listening. So I'm open for questions.
Yeah, I have a question.
Yes, Junqi, can you hear us? Yeah, we have a question here.
Okay.
Can you go back to the slides describing the particles in the box?
Okay.
I was wondering, in this case, do you want you want to find a distribution of the particles which have the lowest energy, right?
Actually, that could be a problem. Here in this plot, I just show a general idea. You can solve, yes, just like the first slide I show for the water molecule, you can also solve the ground state of this many particles. But I think that would be trivial for argon particle. Yes.
So if you want to find a distribution with lowest energy, how can you do that using Monte Carlo simulation? Can you give me more information? Because you don't have the kinetic energy, so the particles can't move, right? So you just get initial state and then give every particle how to say a movement and judge it is accept or not, and then keep on doing this process, right?
Yes, You just described the exact process for Monte Carlo simulation. Yes. We can start like put every argon article on the lattice as an initial guess for your position. Remember, Monte Carlo basically describe a computer experiment. So you randomly pick up an atom, you try to move it. Whether you accept it or not is depend on this Boltzmann factor, you see, which is e to the power delta E divided by the kT. So if you want to solve your system at a given temperature, you can just update your particle in this way. Eventually, you will achieve an ensemble where you have a canonical distribution of atoms at that specific temperature. But of course, this method is, if you do this way, it may not be the ground state, right? So for the ground state, it corresponding to the temperature at 0, right? So you can gradually decrease your temperature and eventually attain to the ground state. There are many methods that can accelerate this process. How you can start from a higher temperature and gradually decrease your temperature and search for ground state. It's actually, I think it's called annihilate tempering or something. Forgive me if I remember it wrong. But yes, there are methods to achieve that. And you described correctly, for Monte Carlo simulation, there's no kinetic part. So you can update your system any way you want, just according to this transition probability. So the advantage is that it can converge faster than MD. The disadvantage is that the dynamics is artificial. Of course, it's artificial. You just update it in a random way. So I hope that answers your question.
Okay, thank you. So when will you stop? I mean this process.
You stop when you achieve equilibrium. For example, you can define a observable you want to measure. For example, you just measure the energy of the system every certain times. You can see there's a curve of the energy either going up to the low. At certain stage, it will go flat. Then you know that the system achieves equilibrium, right?
Thank you, Junqi. Now we're gonna have Reuben.
Okay. Okay, so we're going to switch gears a little bit here, and I'm going to talk a different aspect of physics. My background is in astrophysics, so I'm going to talk a bit about HPC in astrophysics and some of the research that we've done. Junqi mentioned the 3 pillars of scientific exploration nowadays, where we have theory, experiment, and simulation. And I'll show some example where these 3 are interrelated and how simulation supports both theory and experiment. So as a start, I'll start with this theory of gravitational wave, which is it's a phenomena predicted by the Einstein theory of general relativity that he discovered in 1915, basically. And by word of the author Marcia Bartusiak, it's Einstein Unfinished Symphony. Basically, this is the last thing from GR that's not yet directly observed or directly measured. So gravitational wave is the effect of space-time curvature due to mass. In the Newtonian world, gravity is a mysterious action at a distance, but in the Einsteinian world, gravity is the effect of the space-time curvature. So the consequence is an accelerating massive object produce ripples of space-time curvature, and this in effect produce what we call gravitational waves. As I said, it has not been directly detected, but we have detectors that are already online nowadays. We have LIGO that will soon become advanced LIGO. We have Virgo and Geo 600. This is all over the world. And if we can detect gravitational wave, which we appreciate that we will, it will be a novel way to see nature complementing the electromagnetic waves, where in astronomy we've seen nature through visible lights and infrared and X-rays. Gravitational wave would be a completely different way to observe nature. So what's the issue here? The issue is that gravitational wave is very, very weak and very hard to detect, and all of the detector basically works by extracting weak signals from background noise. Now, in order to extract these signals, we need to know, they need to know the templates, what kind of signals we expect from the sources of the gravitational wave. So here's some example of the sources of gravitational wave. The coalition of massive black holes and the rotating neutron star. Remember, this is accelerating massive objects, and supernova explosion and the merger of neutron star and black hole. So as you can see here, this is frequency versus sensitivity to gravitational wave. We have advanced LIGO, which can detect this kind of object, and LISA was used to be in the plan. It's supposed to be able to detect object with lower frequency. Not sure how the fate of LISA knows, but in any case, all of these are very a producer of gravitational wave, but the experiment itself, LIGO or Virgo, needs the template to know what kind of signals to express. So where do we get the templates is where the HPC simulation comes into play, right? This is where we can do a simulation of this phenomena, then we can give it to the observers to know what kind of signals we can expect from gravitational wave. So just as an example, I'll talk about a little bit about binary neutron star merger simulation that I did. So what is a neutron star? This is a dense object left behind by core collapse supernova, and later on we'll talk about core collapse supernova. So as comparison, this is the map of Knoxville, and this is a 1 kilometer or 10 kilometer radius of Knoxville. So imagine the mass of the sun compressed to this area. So it's very, very dense object, and it's usually discovered as a solitary object or as pulsars, and it's also discovered in binary system. So if we have a neutron star binary orbiting each other, it will eventually in spiral because it's losing energy from gravitational wave. So as I said before, this is a candidate for gravitational wave detection. It's also a candidate for what we know as gamma ray burst progenitors. So what do we need to model binary neutron star in HPC? So first we need to be able to do fluid evolution. And because neutron stars usually have magnetic field, then we also need to be able to simulate magnetic fields in fluid. We also need to know some nuclear physics for the equation of state of the neutron star. So this is how we relate pressure and temperature to the fluid equation. We need to implement some form of self-gravity. We can either do Newtonian plus some correction from general relativity, or you can implement a full GR. And different codes implement different things. And the issue here is the cost of the computational cost itself, and how sophisticated is your code that can implement all of this physics. We need to have some radiation transport features, and neutron star merger are inherently three-dimensional phenomena, so your code likely needs to be able to do multi-dimension to be realistic, and the code should be able to resolve different length scale, because we have different length scale from the star surface to the orbital to the outer boundaries. And so to support this, some code use what's known as adaptive mass refinement, where the idea is to put more grid in the places that needs higher resolution. So one of so I guess the major code that I'm working on is called Genesis, and what we want to do with this code is to be able to do things like neutron star merger simulation and core collapse supernova. So we write this code as a code base for large-scale astrophysics simulation. It's written entirely in modern Fortran, in Fortran 2008, and it's object-oriented design, is extensible, and it is grid-based, and it's multi-dimensional. So another way to approach simulation is to use a particle-based code, but it has its own issues. So we choose to use the grid-based Eulerian methods. And we have implemented some multi-physics solver, so it has magneto-hydro capability, and it has gravity, obviously, and it has support for equation of state. And we have some initial support for adaptive mass refinement, where we can refine to higher resolution as needed. So just to talk a bit about how we do simulation in large machines. So the idea here is, this is the fluid equation that we need to solve. It's just pretty simple by itself. So it's a concept, basically a conservation of mass and momentum and energy. So we decompose our domain using for parallelization. So each of this brick is part of a part of the computational domain, and we in HPC, then to run this in parallel, we distribute this domain to different processor or different compute nodes. And as an example here, if we have 20, this is just 27 processor, then each of this brick is sent to different compute nodes. So the code is test driven. So we've tested our code with all kind of available test problem available in literature for fluid and magnetofluid problems. And we've tested, so weak scaling is very important if you run code in HPC, right? The idea is, how does your code work as you add, how does your code scale as you add more work and as you add more processors? So if the code weak scale very well, then you can solve bigger and bigger problem by adding more and more processor. In this case, then you see that the efficiency of our code remains higher than 90%. So meaning communication cost doesn't really produce a bottleneck as we solve bigger and bigger problem and throw in more and more processor. If the code doesn't weak scale, then you'll be having hard time solving bigger problem, because then you're losing efficiency as you try to go to a large scale problem. So we ran our code to do kind of an initial or exploration simulation of neutron star merger. So we use hydrostatic polytrope as a simplified model for neutron star, and each star we give initial velocity using just Kepler orbit. So we kick it so that it can do an orbital. Now we also implement the effect of gravitational wave that remove the energy, so it will eventually cause the star to in-spiral. So at this point, I'm going to show you some simulation movie. So I was going to use my computer, but somehow it doesn't work well with. So I think
I'm just sharing the PDF. So
Oh, you just shared the PDF. Can we share the desktop? All right, so the stars start to in spiral because it's losing, and then now it start to touch each other, and eventually it start to merge to become the spiraling disk of the merging. Now the code doesn't support to evolve black hole yet, but so in this case, for certain mass, then the stars become, but the merging stars become black hole. Okay, so what did we learn from that simulation? So from that simulation, I extracted the gravitational wave signature. And here we can see this is the sort of things that if we detect gravitational wave, will be the sort of templates that we see. So at the beginning, the simulation follows the theoretical gravitational wave for point mass, right? It's almost like point mass because it's just two mass in Keplerian orbit. But then it starts to differ from the point mass, which is the code is the solid line, where you can see this is where you start to see the inspiraling of the star, and this is where the merger happens when you have a sharp peak, and then you set it, and then after the merger completed, you have a ring down, and everything then settles down, and then the gravitational wave projection ceases. So
What is the vertical axis?
the vertical axis, it's no. It's almost like the amplitude of the gravitational wave at certain observing distance.
Okay. So it's representing the oscillation, fluctuation of the.
It's the fluctuation of the space-time itself. Yes. So if you know in LIGO, they have this point mass to detect this oscillation in space-time, and that's what they would measure. So this is the kind of templates that we HPC that provided by HPC simulation for observatory like LIGO and Virgo, so that they can extract the kind of signal from the observation. So here you see that the simulation support the experiment for gravitational wave detection. Okay, now switch gear one more time. So another thing that we can do with the Oracle, we hope to do with the Oracle, is the simulation of core collapse supernova. So supernova is the death throes of the massive stars. So stars that are 10 solar mass or greater eventually will burn all of its fuel and collapse to, and then producing explosion known as the supernovae. This is among the most powerful explosion in the universe, and it occurs about twice per century in our galaxy. And core collapse supernova is important because this is where all the dominant sources heavier than hydrogen and helium are produced. As you can see here, all this bluish element in this periodic table is produced in supernova. So it's really answering the question relating to our origin and the origin of life in the universe. So in the pre-collapse structure of the supernova, as you can see it, if the star is massive enough, it can burn hot enough that eventually it will burn through hydrogen, and which will become helium, and it burns through helium, and eventually it will keep burning the carbon, oxygen, the neon, and the magnesium, and eventually at the center of its core, it's the iron group element. And because iron is one of the most tightly bound element, you cannot extract more energy by burning, so you don't have enough pressure to support the whole stars, and the star is then in the core is supported by the electron degeneracy pressure. Basically, this is Pauli exclusion principle, right? But because there is a neutron capture, eventually even the degeneracy principle lose energy or lose the pressure support, and the core began to collapse. As the core collapse, it goes through the density increase very much so, and eventually it hits what we know as the nuclear density. And because of the strong force, you cannot compress it anymore, and it produces the whole core stalls, and it produces shocks, and the shocks propagates outwards, just like if you compress punching ball very much and it produces shock. The shock propagates outward, and eventually this is the shock that will disrupt the whole stars. Now, the problem is that from simulation, we know as the shock propagates outward, it's losing its energy because stuff is still falling into the core, and because there's a more neutron capture, then the shock lose energy. So the question is, how is supernova shock wave revived? And so that's basically the gist of the supernova problem. So one of the things from doing simulation of core collapse supernova, one of the things that we found out is that the star shock wave that I talked about earlier is actually non-stable against linear or against any perturbation. So this is actually observed in simulation, and this has been observed by different codes that run different simulations. So the question is whether this is the key ingredient to robust supernova explosion. Another thing that we not sure very well is the magnetic field in supernova. As we know, most star has magnetic fields, but then there's a question that, well, as I mentioned earlier, the remnant of supernova is a neutron star, and a spinning neutron star is basically pulsars. And the question here is that the progenitor of supernova usually have weak magnetic fields, right? But pulsars that we observe in nature have very strong magnetic fields, and amplification of magnetic field usually relies on fast rotation. But as we can tell from our observation, that most progenitor stars of supernova usually only rotating slowly. So the question here, what is the role of magnetic field in supernova dynamic, is not clear. So what we want to answer is whether this instability in the supernova star shock wave can amplify the magnetic field of the progenitor stars. So what we found out from simulation is that, in fact, the magnetic field are amplified exponentially from the instability of the supernova accretion shock. So here, this is an example where simulation is fitting the theory of the core collapse supernova, and in fact the theory in the magnetic field amplification in supernova environment. So here's another simulation movie. So the initial condition here is the star supernova shock wave, and then we with some magnetic field, and as you can see, this is the magnetic field measure, volume rendering of the magnetic field. As you can see, initially all of the magnetic field is pretty much a weak magnetic field, only 10 Gauss, and we perturb this initial condition with non-radial perturbation, and we see whether or not the magnetic field is amplified. Go to the movie. And this is where the instability start to kick in. Initially, it's only oscillating, and then eventually a more non-linear instability comes into play, and now you can see that the whole shock wave has rotation. We didn't start with rotation, so rotation is generated here somehow from the instability. See if we can play it one more time. All of this in the time scale of, this is the time scale at the top, hundreds of milliseconds.
So is there any kind of conservation of
Yes.
momentum?
Right, yes, so that's actually a very good question. So how do you know that your code is, I guess, in some way, how do you show some correctness of your code, right? And one measure of it is you have to track the energy conservation and the momentum conservation and all that to make sure that your code is not just wildly do something incorrect. So we do track all that, and we make sure that we conserve energy and conserve momentum and mass.
So the final collective behavior of this type of rotation is actually come from very small amount of residue leftover momentum from the initial chaotic state. Is that?
Yeah. Yes, from this perturbation there. So there is some stochasticity here also. So what's most interesting is that, so this is the kind of thing that was actually found from simulation and not from observation. So what's interesting here is that this perturbation can kick the what's initially non-rotating. Now we know that in real life, stars rotating slowly, but we start with a simplified initial condition. We start with no rotation at all, but in the end, it actually generates rotation because of this instability. So this actually also, there's another article in Nature that proposed that this is from our, that this actually can kick the neutron star into this rotating pulsars, and one of the, so it answers the question about the magnetic field amplification, and also answer the question about where the very high rotation comes from.
Can we understand like initial star is gigantic, so even very tiny type of rotation, it's collapsed to a tiny small one, then the speed will be accelerated due to the compensation of the moment, the angular moment. Is that the picture you're trying to show?
Well, what we showing here is that there is a phenomena called this stationary accretion shock that's non-stable to perturbation, and this instability is basically what generates this rotation. So just slide elaboration of this movie. Here's some slices on the XZ plane. So originally it's only slosing up and down in this perspective, but as it's slosing up and down, the infalling material, the collapsing star, the collapsing stars is hitting this surface, and that's generate more perturbation, and eventually it generate this rotation. And if you look at this picture, this is where the magnetic field is getting more and more intense, and the magnetic field amplification is usually comes from the stretching of the fluid element. So because the instability produce this sloshing, this rotation, it basically stretches the magnetic fluid, the magnetic field. The magnetic field is embedded in the fluid. As it gets stretched, then it gets amplified. And in our simulation, actually, the amplification stops because we have finite resolution, and we cannot resolve thinner flux flow. So in this case, we actually run the highest resolution that we run is 1024 cube. So we ran with over 1 billion cells on 64,000 processors. So, and it costs hundreds of thousands of CPU hours, obviously. So even in this case, we still cannot resolve the thinner flux flow further. So had we been able to run with higher resolution, we probably see even more amplification, but we haven't done that. So one other neat thing that we did, as you see at the end of that movie there, we have this pretty complicated magnetic field. So what we did is that we look at the surface of the shock, and then we put a random seed and on the surface, and then we trace the magnetic field lines on those surface, and we want to see how does the magnetic field lines looks like. So this is the next visualization shows that.
Flux line.
Yes. Uh-oh. Let's scroll down. This is from this simulation. This visualization comes from the same simulation result that I showed earlier. Hello?
Yeah.
Okay. So this is the surface of the shock wave. And we put some seed. And then we just trace the magnetic field line from in the center. There is the protoneutron star. Okay.
What do the flux lines tell you?
I'm sorry?
What do the flux line tell you?
That it's a pretty complicated structure of magnetic field inside the supernova environment. But the neat thing here is not only the simulation itself takes a lot of computational cost, the visualization also takes a lot of a lot of computing cost, because you have to get the terabytes of data from the simulation data, and then you have to run through the rendering, get this kind of thing. But without visualization, we cannot understand what the simulation tells us. I think that's all my talk. Thank you.
Thank you.
Thank you.